NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hello and a very pleasant good evening to you wherever you may be. I am Brian White from JPL's Office of Communications and Education, and welcome to the final Von Karman Talk of 2022. From Star Trek to Kurt Vonnegut and all the sci-fi in between, people have dreamed of planets beyond our home, beyond our system. In the past 30 some odd years, these dreams have become more of a reality with the field of exoplanet discovery. In this scheme, the nearest known exoplanet orbits Proxima Centauri, the next star over from Earth, and it's a little more than 4 light years away, or 24 trillion miles. If an airline offered a flight there by jet, it would take you 5 million years to get there. However, exoplanets offer a unique view of our solar system and of our home planet. Now, I'd like to introduce our questions co-host for tonight, a public outreach specialist here at JPL, Dr. Nora Bailey.
Thanks, Brian, and hello, everyone. Remember, this is your space program, and we really want you to be involved with this conversation. So if you're watching on YouTube or Facebook Live or LinkedIn, you can go ahead and submit any questions into the chat box right there, and our social media team will bring in as many as possible as we can into our talk tonight. If you don't see the chat box, go ahead and reload the page, and it should be right there.
Thank you, Nora. Now, our speaker tonight is a technologist for the Nancy Grace Roman Space Telescope, CGI. She received her PhD in astrophysics from the Université Joseph Fourier in France, was awarded JWST time through several GO programs, including one as a PI. And when she's not working, you can find her exploring national parks from Yellowstone to Mauna Loa or to the Everglades. Please welcome Dr. Marie Ygouf. Hello.
Hello, Brian.
How are you today?
Very good. Very pleased to be here.
Well, it's wonderful to have you here. Let's just dive in. Let's start with the main topic. What are exoplanets? What are we talking about tonight?
Yeah. So exoplanets are planets that are located outside of our solar system. Those distant worlds are extremely diverse, and although some may look very similar to the planets of our solar system, we know for sure that some of them are actually pretty different. So let's have a look at the first slide, please. Yeah, so as a reminder, we have two types of planets in our solar system. On one side, we have the small rocky planets that are also the closest to the sun. They're called Mercury, Venus, the Earth, and Mars. And on the other side, we have the gaseous giant planets that are also the furthest from the sun. They're called Jupiter, Saturn, Neptune, and Uranus. And before discovering the presence of exoplanets, the solar system was the only model of planetary system we could think of. And it was very hard to think about other models of exoplanetary systems.
So with that, of thinking of ideas of different models and different systems, how are these exoplanets teaching us about our solar system?
Yeah, so one thing we learned by studying exoplanets is the existence of planets that are dramatically different from the planets of our solar system. So on slide 2, we can see it. So the first planet discovered around a solar-type star in 1995 by Nobel Prizes Michael Mayer and Didier Queloz was a pretty different kind of object. It's a gaseous planet, much larger than the Earth and situated much closer to its star. And it only takes 4 days to complete its orbit around its star. And as a comparison, Mercury, which is the closest planet in our solar system, orbits the sun in 88 days. So this type of planet is definitely not something we can see in our solar system. Could you bring also slide 3, please? And so since that discovery, we found many other exotic planets that don't have equivalent in our solar system, such as an entire new category of planets of size between the size of the Earth and the size of Neptune, that we call either super Earth or mini Neptunes. We also have lava worlds, puffy planets that have the density of styrofoam, and also dense core of planets that are still orbiting their stars, but without any atmosphere. We also have planets orbiting groups of stars, also orbiting dead stars, and even rogue planet that doesn't even orbit around the star. We have highly eccentric planets, and in fact, many of the exoplanets discovered so far have a higher orbital eccentricity than the planet in our solar system. So studying those exoplanets teaches us a lot about our own solar system. For example, it is very possible that we had a super Earth in the past that would have been expelled from from the solar system, or also collided with a gas giant. It's even possible that it's still here somewhere and we haven't found it yet.
Well, you talk about all these different types of planets that we kind of don't even think of in our solar system. How many planets have we discovered?
Yeah, so can you bring the slide 4, please? So as the 1st of November, there were more than 5,000 confirmed exoplanets and more than 9,000 candidates needed to be confirmed. And one telescope that revolutionized exoplanet detections was Kepler, the Kepler Space Telescope that was launched in 2009. And one of Kepler's findings is that there is at least one planet on average per star. And as a matter of perspective, our galaxy, the Milky Way that you can see on this picture, has a couple of hundreds of billions of stars. So that means that we discovered only a tiny, tiny fraction of exoplanets in our galaxy. So there is quite a lot of room for incredible discoveries out there in the field of exoplanets. So to diving a little bit more, let's have a look at the slide 5, the discovery timeline of those exoplanets. So this figure shows the number of detected planets as a function of time. And we can see that this number is increasing as an exponential speed. The first discovered planet was in the 1990s. And as you can see, this is a pretty young field. I mean, it's less than 30 years. And exoplanet discovery is almost routine now, we can say that. And because those years, we discovered one planet every 2 days in average. So, of course, this was not linear because we started with a pretty small discovery rate, and then the dedicated missions were built to detect those planets. And with every new mission, the yield of planets grew larger and larger.
So if that yield's growing larger and larger, we're finding them exponentially. How do you find them? How do we discover these planets out there?
Yeah, so another thing that we can see on that figure is that the majority of detected planets have been discovered using 2 main techniques, the radial velocity technique and the transit technique. So we'll see what are those techniques. So first illustration 6 will show a little movie of the radial velocity technique. So with that technique, we detect the tiny movement perturbation an exoplanet has on its star. That slight movement affects the star's normal light spectrum or color signature, and the spectrum of the star that is moving toward us appears slightly shifted toward bluer and shorter wavelength, while when the star is moving away, its spectrum is shifted toward redder and longer wavelengths. So that's for the radial velocity method. And in the next movie, we'll see the transit technique, how it works. And so with that technique, we measure how the luminosity of a star evolves over time. So most of the time, that luminosity is constant and quite boring. But some variable star, we will see in those variable stars that this luminosity can vary in a random fashion because of the activity of the star itself. But in some very rare occasion, we can see periodic decreases of the luminosity of that star, which indicates that one or several planets are passing in front of the star. So those techniques are what we call indirect technique, because exoplanets are detected through the indirect effect they have on their host star, but we don't actually see the planet themselves.
Well, if you're calling these indirect techniques, if we flip the coin, do we have direct techniques? Are there more direct ways to find these planets?
Yeah, I'm sure you're gonna ask that. So yeah, Alpha, this is pretty challenging, as you can imagine, but we'll see that. There's another technique some astronomers and myself in particular interested in. This technique is called direct imaging, also called high contrast imaging. And so what is interesting with this technique is that we can actually get picture of those worlds. And this is a game-changing technique because, first of all, the type of exoplanet that we can detect with this technique is very different from the exoplanet we can detect with other indirect techniques. The second thing is that we can know exactly where the planet is and learn about the orbits of those planets. And finally, we can directly probe the chemical component of that atmosphere at different wavelengths and learn crucial information on those planets, such as their mass, their gravity, and whether certain chemical components are present in their atmosphere. So let's pull out illustration 8. Now we have only a few pictures of those exoplanets so far. And the reason is that it is pretty challenging. See, because the star is so bright that we first need to block its light to be able to see the light of the faint planet. And we're doing that by using a very small optical component that is called a coronagraph that acts similarly to what the moon does to the sun during a solar eclipse. So we can see on illustration 9 a picture of such a solar eclipse. And if you are lucky enough to have experienced a solar eclipse, I really recommend that. See if you have the chance one day. You may have noticed that we can see stars in the middle of the day. And with a coronagraph, we can do the same with any star and hunt for planets that orbit around them. But the extreme contrast of flux between the planet and its star is not the only challenge we're facing. We also need enough resolving power to be able to separate angularly the planet from the star in the image formed by the telescope. And for that, it really helps to have a big size telescope. And it also helps to observe stars that not too far from us, which limit a little bit the number of targets that we can observe with that technique. And one of the other challenge of direct imaging is that we need telescopes that are sensitive enough to detect the very faint signal from the planet. And here again, telescopes with big mirrors help for that. And also telescopes that are in space are sometimes more sensitive than telescopes on the ground, depending on whether we are observing in the infrared, the visible, or other wavelengths.
So you're talking about these different wavelengths, you're talking about these, I mean, it sounds like there are a lot of challenges in order to try to discover anything out there.
Yeah, there are definitely a lot of challenges. So let's have a look at the illustration 10. I would like to show you a video that illustrates how we solve the contrast issue with a coronagraph. I think it's a very, very nice video. So you'll see here an exoplanetary system orbiting a star, and you want to observe that system with a telescope. So the light is going to go through the telescope, and we're going to see what's happening inside the telescope. So here, the light is going to first reach a mirror and then a couple of optics and create the image of the star on the detector. And then you have a chronograph that you put in there to remove most of the starlight. So that's one component of the chronograph, a second component of the chronograph, and you see that the light disappear. And then you can ask, but it will hide also the planet, but that's not the case because the planet is off axis and is not hidden by the chronograph. It's not blocked by the chronograph. So there are 2 planets in there, but we cannot see them because there are a lot of residual, instrumental aberrations in the instrument that prevent the chronograph to work optimally. So we want to correct in real time those instrumental aberrations with a deformable mirror to be able to further remove the residual speckle or residual starlight that we can see on the image. And it's much, often not sufficient because we also need to use and develop state-of-the-art post-processing technique to further remove the starlight. So, yeah, I'm pretty sure that now that you have, you know a little bit more about how those chronograph works, you would like to see what it does in reality. I mean, what a real picture of exoplanets. So let's go to the slide 11 that shows an actual movie, not even an image, an actual movie of an orbital, an entire exoplanetary system that orbits the star HR 799. So I think it's a particularly stunning video because you have to imagine, this is a system that is at 130 light years from us. And the HIT 799 star hosts not less than 4 giant planets that are about 10 times more massive than Jupiter and approximately the same diameter as Jupiter. And as you can see, we're pretty far from the artist's concept illustration that we're seeing all the time on the internet for exoplanets. We currently don't have the capability to take such pictures, but what you have in front of you is what we can do currently, and I think it's still pretty amazing in my opinion.
It is pretty amazing. I could watch this all day as they orbit around. You talked about the star called HR 8799. Really rolls off the tongue there. How do some of these exoplanets get their names?
Yeah, so exoplanets can actually have several names. Okay. So the most conventional way, or at least the way astronomers call an exoplanet usually, is by using the name of the star plus some minor case letters. But planets are sometimes called by the mission that discovered them. That's the case, for example, of the Coro mission, the Kepler mission, or the TRAPPIST telescope. And the letters, they are usually given by alphabetical order in the order of the planet discoveries. So let's take the example of the TRAPPIST-1 system on illustration 13. Yeah, it's not the good one. Sorry, 13 should be, yeah, okay. Yeah, that there's any issue with the numbering anyway. So if we go back to the movie of the HIT 799 exoplanetary system that we were showing just before, yeah, exactly this one. So if we take the example of this movie, the planet that is the furthest of the star is called HIT 799b. And then after, the one that is a little bit closer is called HIT 799c. And then we have HIT 799d and HIT 799e. And the reason for that is that the planet that is further from the star is the one that is the easiest to spot in direct imaging, because the better we get at developing post-processing technique, the better we are, and we can remove the residual starlight and be able to detect the planets that are closer to the star. But for example, if we take the example of the TRAPPIST-1 system, which is the one that we saw just after, I think.
13 or 14?
No, not even. Should be 14 on my, yeah, great, thank you. So this famous exoplanetary system was discovered with the ground-based TRAPPIST telescope using the transit technique. And the first discovered planet was planet B, which is the one that is closest to its star. So it's different from what we saw just previously. And then comes C, D, E, F, G, and H that were successively discovered. And the reason why the first planet to be discovered in the system are the closest is that they were discovered using the transit technique, as I said, for which it is actually easier to detect the planets that are closest and more difficult to detect the further planets. So, yeah, let's see. I think we can switch to the next illustration then. Yeah, which is this one. Awesome. So one thing I wanted to mention, which is a cool thing, is that the International Astronomical Union make possible to the general public from the entire world to choose the name of a subset of exoplanets. And there were a couple of rounds in 2015 and 2019. And the latest round to name exoplanets is still going on at the moment. So if one of your dreams has always been to name an exoplanet, I will really suggest to go for it and check the website, the Name ExoWorld website that should you should see on your screen. Sorry, and check that website.
I've always wanted to name a planet. There's all sorts of things I wanted to name. So I'm going to go take a look at that after this. So that's what's down the road for me. But what's next down the road for exoplanet and exoplanet discovery?
Yeah, so next slide is should be a nice summary of the major exoplanet missions. So the past, current, and future missions. And if you look at the top right, you will see a space telescope that has been recently launched and commissioned, the James Webb Space Telescope, or JWST. And after JWST, the next down the road will be the Nancy Grace Roman Space Telescope, a Hubble-sized telescope that will be launched in 2026, and that will cover some great exoplanet topics. So let's dive a bit more with what's coming in the next 10 years. So next slide. How not to mention the first exoplanet image with James Webb. And this has been recently imaged, right, that there are image as of the planet HAP 65426b that was released about 2 months ago. So this planet is a 9 Jupiter a 9 Jupiter mass planet that is at 385 light years from Earth. And it was discovered in 2017 with the Sphere instrument on the VLT. And this planet was chosen to be a prime target for James Webb because it is at wide separation of its star and thus pretty easy to spot with JWST. But we expect JWST will discover new exoplanets by dozen pretty soon. And for example, in the next slide, we can see an example of target that we will observe with James Webb, and you can recognize the HRT 799 system that we talked about earlier. So we will observe that target very soon with James Webb, and we will not only further characterize the exoplanet, the 4 exoplanets that are in that system with those observations, but we also will look for new planets in this system. And there will be also many other systems that will be observed as well. So we don't expect James Webb to find thousands of exoplanets like previous missions such as Kepler or TESS, because this telescope is not dedicated to exoplanet science. JWST is going to do a lot of other great science besides exoplanets, even if maybe we can expect that 25% of JWST time may be on exoplanet science. But we expect great discoveries in the field of exoplanet characterization, like illustration. The next illustration is going to show. So, okay, it's sorry, it's not this one. It should be the spectrum of James Webb.
I think that is number 19.
Yep. Excellent. Thank you. So this illustration, this figure shows the spectrum of an exoplanet, which is called WASP 96b, which is a hot gas giant exoplanet. And it has half the size of Jupiter, and it orbits its star every 3.4 days. And it's located at 1,150 light years from us. And JWST was actually able to detect water in the atmosphere of this planet, which was apparently quite unexpected for that particular object, because it was previously thought to be cloudless, completely cloudless. So it was quite a surprise. And JWST will probe the atmosphere composition of many known planets to identify chemical components such as water, methane, or carbon dioxide. And it's going to do that with a lot of known exoplanets. And it really opened the path to statistical analysis of those exoplanets. And so with this capability, we hope to learn more about the composition of exoplanet atmospheres, and then how they were formed, and also learn more about the planet in our own solar system as well.
James Webb is kind of, it's astounding, and the images and everything we find from that. But I want to talk about what you're going to be working on, the Nancy Grace Roman Space Telescope. Can you tell us more about that with this field?
Yes, of course. So yeah, next slide should be the Roman Space Telescope slide. Yep, awesome. So Roman is the next big NASA mission to be launched in 2026 with 2 different instruments. So first we have a science instrument, which is called a wide field imager, that will detect thousands of new exoplanets using the techniques of transit and microlensing. And second, we will have a technology demonstrator, the Coronagraph instrument, that will demonstrate the key technologies that we need to image terrestrial planets in the habitable zone of their star and characterize their spectra. So you can see, for example, one image, simulated image of what we could see. You might think, okay, it's not. It doesn't seem better than what we saw already, but there is actually a big difference. Is the contrast that we were able to reach with Roman is several order of magnitudes the contrast that we are able to reach right now with the current instruments. So with the current instrument, we can do contrast of 10 to the -6, for example, but here we're going to be, with Roman, we're going to be able to observe planets with contrast to 10 to the -9. And that's all this while demonstrating the technologies that we will use to to detect terrestrial planets using direct imaging in the future. So the next slide will show that this Roman telescope will open the path to the next generation of space-based telescope that will look for signs of life on exoplanets. But for those telescopes to become reality, there's still a lot of work to go, and we'll have to be patient and wait at least 20 years or more.
That's amazing, and it's astounding, and I'm looking forward to everything that you find with that telescope. The audience have been asking amazing questions tonight, so I'm going to throw it over to Nora, and let's get these audience questions in our talk tonight.
Yeah, thanks, Brian. This was a great talk, and there have been so many awesome questions from our audience. So Cyclops on Twitter asked, is there anything in the works to send a spacecraft to any of these exoplanets?
Yeah, I've heard about some projects that could visit some of the planets that are the closest to us. So the planets in the Proxima Centauri system, which is the star, which is our neighbor, basically the star that is closest to us. However, it's a star that is located at 3 to 4 light year. So that means that if we were to go to that star at the speed of light, it will take us 3 to 4 years to go there, but we are pretty far to go at that speed, and so it's for now a little bit out of reach. But there are definitely some projects, and people are thinking about that because it's like a fun thing to think about visiting another exoplanet.
Yeah, Donnie on LinkedIn actually asked, would we ever send humans, not just spacecraft? Do you think if we had the advanced technology, would we be able to send humans there as well?
Yeah, so same kind of the same answer here is that we don't have the technology for now to even send a spacecraft. So I'm pretty sure if we had the technology to go, some people would like to go, but yeah, it's definitely it's already a challenge to go to Mars, right? Or even to go back to the moon. So yeah, it's definitely not the same distance. So yeah, it's not for tomorrow. And then people in our generation are probably not gonna see that in our lifetime.
Yeah, it'd be a long trip. So Vector on YouTube asked about the TRAPPIST-1 system that you were talking about. Is it possible that there are planets that are either really small or on tilted orbits that exist in that system and we just don't know about them because they haven't transited?
Yeah, it's totally possible. I mean, anything can be possible. It's possible that there are some, gravitational interaction in a system between some planets that makes a planet change orbits and have an inclined orbit. That would be possible. But we don't know, and that's one of the advantage to use several techniques to observe the same system because they are complementary, right? So if we don't detect with the transit because they are not in the same same plane as the other planets, we could, for example, detect another planet in that system using the radial velocity technique, or even direct imaging if we're lucky. But the TRAPPIST system is a little bit far to be accessible for direct imaging, but who knows, someday. Yeah.
Awesome. Zaker on LinkedIn, as well as Cyclops on Twitter, both asked about how we actually identify the chemical composition of these exoplanets, like you were showing with the JWST spectra.
Yeah, that's a great question. So to do that, we have two techniques. So the first one is to observe the same system using different filters at different wavelengths. So that gives us some clues about the composition of those planets. So that's something that we're going to do on James Webb. using, for example, the NIRCam or the MIRI Coronagraph that we have on James Webb. But we don't have the capability to do a spectrum using direct imaging because we don't have a prism on the instrument that have the chronograph. We have some spectrograph, which are kind of prism, elaborated prism on instruments that we are using to disperse the light that we receive from a planet or a star to create those spectrums. So this is how we create those spectrums. So here, as you can see on the top right, the spectrum has been done using the NIRISS instrument on James Webb. And this has been done using the transit technique in particular. On Roman, it's going to be a little bit different, is that we're going to combine a coronagraph and a spectrograph so that we will be able to not only do some direct imaging and see pictures of those planets, but also we will have the capability to take those pictures and put them in a spectrograph and also extract the spectrum from that star. So this is why this technology demonstration is so important, because combining the coronagraph and the spectrograph will give us the capability to really observe and characterize the atmosphere of those planets.
Thanks, that's really exciting. Really looking forward to Roman. So Tom on LinkedIn asked if there's any kind of special exoplanet science that can actually be done taking advantage of being at the Lagrange points, such as L1.
Oh, L1 or L2 maybe, or whenever. Yeah, I mean, all exoplanet science can take advantage of being at that point because those kind of points are gravitationally stable point in space that offer much stable condition for observation. And so when we observe exoplanets with any kind of technique, basically, the more stable a telescope is, the better, right? So that's one thing. And if we want to increase the detection capabilities, we want to spend more and more time on those planets. So we want to be as stable as possible because you're going to stay for a long time on those planets. And the second great advantage of going to L2, for example, such as JWST is at L2, Roman will be at L2 as well, is that we the telescope is going to be further from the Earth, and the Earth is a kind of a black body that's going to emit a lot of infrared light, and this is also, for example, the wavelength in which James Webb observes, right? And so you don't want to, I mean, the Earth is pretty bright for James Webb because it's observing in the same wavelength that the Earth is emitting. So the further you are from the Earth, and the better it is for exoplanetary science, in particular for James Webb.
Awesome. So Sarenga on LinkedIn asked, out of all of the exoplanets discovered so far, how many closely resemble Earth in terms of atmosphere and land or even water?
Yeah, there are a couple of parameters, I mean, ingredients, we'd say that we are looking into. And so first, you need to have a terrestrial planet, a rocky planet, to be close or similar to the Earth. So that's one thing. The second thing is you have to have an atmosphere. And the third thing is that if we want to find something similar to the Earth, we want to find a planet that is located in the habitable zone of its star. So that means that this is a zone where water can exist in liquid form, and that could be some very conditions for the life to develop in such a planet. So for now we know that there are some terrestrial planets that exist in the habitable zone of their stars, but we still don't know if those particular planets, and there are a couple of them, there are not many, but there are a couple of them, we know about a couple of them, and we don't know yet if those particular planets have an atmosphere still. And so that's one of the questions that James Webb will have to answer, actually, by pointing some of the planets that are in the TRAPPIST-1 system that are pretty good candidates for that. So we'll learn more with James Webb.
That's really exciting. That's one thing I love about exoplanet science, is there's just so much left to learn. So we just have time for one last question. I think this will be a great one to end on. This is from Anaya on YouTube, and she asks, how did you know you wanted to study this topic, and what tips would you have for a younger person or anyone who's interested in astronomy and astrophysics?
Yeah, that's a great one. So I always been obsessed kind of by astronomy. When I was like super young, I was always looking for the moon, and so I kind of knew, I mean, that I liked it, but I didn't know that it could be like a job, right? And so I discovered that when I was a teen, reading a science magazine, and I discovered that you could actually be an astronomer and study this as a job. And that day I figured out that that's what I wanted to do, right? And I didn't know that I would wanted to work on exoplanets, because at the time we hadn't I'm that old. At the time we didn't know that exoplanet existed. And so I was lucky to be here. I mean, to be around when and pretty, I mean, that young when we discovered the first exoplanet. And so I followed all that stuff, and I had the opportunity when I was a student to do an internship at the Observatoire de Paris. So it was in France, and this internship was in exoplanets. And since that day, I knew that I wanted to be an astronomer. I didn't know what kind of astronomer I wanted to be. But that day I said, okay, the planet is so cool. I just want to to be part of it. And to answer the second question about is there any tips, I'd say one of maybe the best tip I would give is that if you know you want to do something and you're really passionate about it, and it's part of you kind of, you should really persevere, because it's very hard. There are a lot of obstacles, and it's only by persevering that you can reach those goals and be able to do what you want to do.
That is a perfect way to end tonight. Unfortunately, everyone, that is all the time we have for this evening. I do want to thank our co-host, Dr. Nora Bailey, and our terrific speaker, Dr. Marie Ygouf, for their joy and their expertise. We also want to thank Christopher, Colin, Max, Bill, Gabby, Mark, Curtis, Nikki, Joey, and everyone that you don't see, but they're there monthly behind the scenes who make these public talks possible. Our final thank you is to you, the audience, who join us every single month. This is your space program, and we're grateful you invite us into your lives every month with these Von Karman talks. Our next talk will be in January of 2023. Thank you again to our speakers. Stay safe, stay kind, stay curious, and we'll see you next year.